Hello everyone, I'm Borja Pérez from Universidad de Cantabria, and it's my pleasure to be the chair for this session in which we have 5 very interesting talks. And let's start with the first one, which is from Lucana Santos from ESA. She is a microelectronics engineer, and her focus is digital IP and microprocessor design.
Thank you very much. First, I would like to thank you for giving me the opportunity to be here and give you an update on the latest RISC-V microprocessor developments we have for space. I want to start where my colleague Roland left it in 2023. At that time, he mentioned at the end of his presentation that there were 2 missions that we knew about flying RISC-V. To the date, we know that there have been at least 3 more launches, and I'm sure there are more. We are the European Space Agency, but we don't know everything. And this shows a little bit how RISC-V is consolidating also in space. You might be wondering, why do we do specific developments for space? And this is because we have some technical constraints. One of them, and the main one, is radiation. So there is ionizing radiation in space that can affect integrated circuits. It can destroy them. It can cause upsets. And this makes it possible to use commercial off-the-shelf component, but we need to do a lot of testing and screening, and they end up being very expensive. So what we many times do is we add mitigation techniques, maybe at RTL design, or also we use radiation hardening by design technologies. This can be error-correcting codes or triple modular redundancy. Other challenges come with the fact that we operate in vacuum, that the circuits are subject to a lot of vibrations, or they have to sustain very wide temperature ranges. And also the lifetime of the satellites is very long. It's up to 20 years, and this is a very long time where we cannot do any repair. There are other functional constraints. Many times we need determinism, and you will see mixed criticality software being used. And we also use some specific interfaces that were developed for space applications, such as space wire and space fiber. Besides that, there are also economical and organizational constraints. The part count that we have is very low, and in a successful project, we have tens of parts maybe being used. The product cycles are long, and we face that sometimes engineers are gone in the process, or companies, they close. The supply chain becomes very expensive because, among other things, we have to do space qualification. This means many times destructive testing. And it's also difficult to attract commercial players. For example, the foundries only support high-volume products many times. And the IP royalties tend to come very late, too. And there is also a challenge related to public funding. We are the European Space Agency, so we have our own funding schemes. There are also funding from the European Commission or from other national bodies, and they all come with their own rules for how to spend the money. Since the very beginning, when we started developing microprocessors for space, we saw the importance of an open instruction set architecture, which allows for competition of multiple IP sources, and it helps us to also apply these mitigation techniques to a design, brings academia in the game, and warrants for flexibility and non-dependence. And the big example of that is Spark, which has been very successful. We have 5th generation of Spark-based microprocessors in space, and there have been many flight parts shipped, and there is a mature software ecosystem. But Spark is becoming obsolete. There are less and less users. And we see the importance as ESA of the instruction set architecture, and that is one of the main advantages that RISC-V is bringing to us, but also the huge and growing developers community. In the first RISC-V in Space workshop that we organized, we had 70 people attending, and this year this was 180 attendees. It's also important that there is a huge open hardware community. There are a lot of open source IP cores. We started evaluating RISC-V on open source IP cores, and this is just a list that we needed on cores that he found could be useful on several repositories, and they all have commits from the last year. So showing a little bit into the developments that we have, the GR765 will be the first rad-hard microprocessor based on RISC-V. It is a transition core. It has Leon 5 Spark processors and no-LV RISC-V. The user can decide if to use one or another with a bootstrap signal. The no-LV is a dual issue in order 7-stage pipeline. It includes many instructions, many of the instruction sets. And recently we also got some performance metrics by Frontgrade Geisler on the no-LV core. Another important feature is that it will include SIMD sections. This was development sponsored by ESA for Leon 2, in fact, but we have ported it to no-LV. And these extensions are basically the computation of a single instruction on multiple low-resolution operands. The main objective was to accelerate or to enable the execution of GNSS tracking, but we have extended it to target many applications, including now in the data compression and AI. Other features that we will have in this chip that are related for space is NeFPGA. It's a small FPGA from NanoExplore. A GNSS IP. We are also incorporating security features and, of course, space fiber, space wire interfaces. The first tape out is planned for the last quarter of this year, and we will see prototypes next year. Funding is very important, and there are developments in the scope of the IEEE Space Component Sovereignty for Europe, called the Ultra Deep Submicron initiative, that will help have a European supply chain for integrated circuits, defining rad-hard design libraries and IP cores for 22 nanometers and 7 nanometers. And there are a couple of activities here. Some of them have already started. Some for others, the calls are in preparation, and others are waiting for funding. But related to RISC-V, there will be the development of a next-generation European space processor based on open source RISC-V in 7 nanometers and software tool ecosystem. And also, we will have the development of a general-purpose accelerator based on RISC-V. And this will target applications such as digital signal processing for radar or digital beamforming or AI. So our move to higher performance computing in space will be the GR7XV. This design is at the moment on hold, so it's just at design stage because all the effort is put on the GR765. It will have 16 cores this time, RISC-V of course, and to accelerate the processing it will include a vector unit, vector processing unit, and there will be, we are evaluating also the use of an accelerator, maybe monolithic or system on chip. And the funding depends on the UDSM activities. Besides the design of this system on chips, we are also working on the hardware and software ecosystem and activities aimed at supporting the use of these processors, including the maturation of IP cores. We will have a microcontroller IP core based on RISC-V in the ESA IP core portfolio that we will be offered to the space community, extensions of the software ecosystem, the instruction set simulator, and development of software tool, and also the development of a reference flight board design to assist on verification and validation activities. Regarding the future needs of our space applications, so we need more performance, and because there are more demanding algorithms that are going to be used. Image processing comes at higher resolution. We want to do software design radio. There is more AI and machine learning that is being used, nonlinear functions, and also quantized computation. And yeah, to come up with this, we need to come with new architectures, and there having, for example, space-specific benchmarks will help. We have already a small suite of benchmarks called OBP Mark, but we want to extend it, and to make better architectural decisions, we want to incorporate maybe hardware, software co-design too. And as always, we need to look into fault tolerance and low power for space. We as ESA cannot impose roadmaps. We cannot say exactly what has to be done. We have to make, to have an advisory role and listen to the member state and to the industry. But in the end, what we want is to make a useful product with the people, IP, and fabs that are available in the ESA member states. For the future architecture selection, we need to think a little bit ahead of the user feedback, because it always comes too late. And we have to be flexible for the different application domains that we want to target. We don't have capability to make system on chip specific for a for various applications. And in that sense, we will probably have parallel vector and matrix processing, and we work on 3 pillars: a general purpose processor, good programming logic, FPGA, and a vector processing unit. There are some solutions, or the solutions we go into, for example, things close to the AMD Versal, with domain-specific accelerators, such as the IKEDA IP, out-of-order execution, and of course, everything will be a many-core processor. So we can see that RISC-V has taken over for space. There are several developments being funded, others that are starting, and in the future we hope to see universal low-power European processor for space that is based on RISC-V with large FPGA fabric, with also accelerators. This can be monolithic or chiplet, is still being evaluated. I have shown you how RISC-V is increasingly being adopted in space. Some time ago, a colleague, Gianluca, was in a RISC-V forum asking if buzzwords survive in space. And yeah, we have shown that, yes, RISC-V is in space and will be in the near future, and it's really consolidating. There are chips being developed, and there are more activities around them. But of course, we need continued investment and cooperation, and that will drive the progress in space applications and future processor development. And with this, I finish my presentation. Thank you.